Okay, a quick review. What is a base? What is an acid? It's crucial we understand what that is. Um, a base is something that disassociates OH, called hydroxyl ion. Now, sometimes it's kind of a secondary deal, but it's what we involve with nitrogen compounds, but it still involves OH. And we have strong, weak, and non bases. A strong base, there are two main ones going to be running into sodium hydroxide, NaOH, and KOH, potassium hydroxide. Most of the other bases are weak bases. Lots and lots and lots of weak bases. Most of those are organic bases also. As we speak, we're talking about nitrogen bases in my OChem class. And there are neurotransmitters, there are alkaloids, there are drugs, and all of them have nitrogen in them, all of them. And they exhibit basic tendencies also. Okay. At a counter to that, there are acids. Acids disassociate H pluses instead of OH minuses. Now, an H plus is the same thing as a proton. Because an H atom has one proton and one electron. If you lose the electron, the only thing left is a proton. So sometimes acids are referred to as proton donors, particularly in in a minute, I'll talk about it, but bases frequently are, we'll talk about proton receptors. You have a donor and a receptor, or a donor and a recipient. Okay, so a strong acid, 100% disassociates. Same with a strong base, 100% goes over. A weak acid, a part of it disassociates. Now, with a strong acid, like hydrochloric acid, there is no HCl. It's only H's and Cl's, period. So whenever you see it written, I want you in your mind, I want you to think of hydrochloric acid as that. And that's going to be the main acid we talk about in this class, is HCl. Now, it gives off one H. Some acids give off two, some give off three. Now, just because there's an H in there doesn't mean it comes off necessarily. If it comes off, then it's an acid. If it doesn't come off, it's something else, like ethanol, for example. Where's ethanol? Right here. That's drinking alcohol. It has 6 H's, but none of them come off. So it's not an acid. It has an OH. It doesn't come off either, so it's not a base. So it's neutral. All right, so and then of course there are weak acids. Majority of acids in the world are weak acids, probably 2 or 3 million of them. Most of them are organic acids again. There are more organic compounds in the world than non-organic. Okay, so that's acids and bases again. So let's talk about what happens when throw an acid and base together. Okay, when we throw an acid and base together, the H plus from the acid and the OH from the base form water. Water is extremely stable. So the neutralization reaction is driven by that water stability. Now, whenever you have a reaction, you always have a driving force. And it's usually a stability driving force. So if your product is very, very stable, that's what's driving it. If it's not very stable, your reaction either won't happen at all, or it'll happen very slowly, or barely it'll happen at all. So stability is really an important factor. And I stress this in all my chemistry classes, regardless of the level. Doesn't matter if we're talking about quantitative analysis, which is the third level chemistry. Doesn't matter if we're talking about organic chemistry, biochemistry. It's stability rules. If it isn't stable, it won't happen. Okay. pH is the metric we use to measure acidity. Seven is considered neither acidic nor basic or neutral. Now, interestingly, water is both an acid and a base at the same time, because it's got an H that comes off and it's an OH that comes off at the same time. It's a very weak acid and a very weak base, but it both happens. And there's a number of terms that describe that. One is autoionization. Auto meaning automatic, and it automatically ionizes to a very, very small degree. Okay, now, if the pH, which is a metric of acidity, is less than 7, it's considered acidic. If it's greater than 7, it's considered alkaline or basic. Now, you'll hear this word alkaline used more than basic. Alkaline is a very ancient term from the alchemy days. And it's still used today all over the place. When we talk in chemistry, though, I mention alkaline because most people are familiar with that. A lot of chemistry teachers only will say basic. But think basic / alkaline, same thing. Okay, so let's talk now about some solution chemistry as it relates to acids and bases. All right, so real quickly, measurement of solution is moles per liter. Concentration, and that's uppercase M, italicized. And I boldface it and do all kinds of other stuff just to make sure you don't mistake it for meters. Okay, so strengths of acids are reflected in pH, and pH has molar concentration built into it. So I'm going to write down what pH is, but don't you write it down. It's just to kind of tell you what it is. Okay, so the definition of pH . It's the negative logarithm of the hydrogen ion concentration. And pH, I don't know why, but it's out of the scope of this class. I don't know why don't want me to teach pH, but class up in Sierra, the same class, I teach pH up there. Washington, I taught at Tacoma, I taught pH there too, but anyway. But the guy that's responsible for this class, Dr. Rabati said, nope, no pH. So anyway, it's still a metric though. And we're not going to calculate, that's when you use the logarithm scale on your calculator. We're not going to calculate pH, but it is concentration. They also have pOH as well. In biochemistry, they have P sugars. So the little p, lowercase p, is a negative logarithm of a concentration of something. In the case of pH, it's hydrogen ion concentration. Case of pOH, it's hydroxide concentration. In the case of P sugars, it's the sugar concentration. They use it a lot in diabetic treatment and clinology. Okay. All right. So that pH is fundamentally a measurement of concentration. Although, because it's the negative logarithm, it's kind of weird the way it works. The lower the pH, the higher the concentration. So it's an indirect relationship. And the reason why you say, well, why do we use it at all? Because most of the time we're working with very dilute concentrations of acids and bases. So then the pH works better than otherwise because it's really awkward concentrations. The numbers are awkward. So it's a very convenient way to write really small numbers is with the P. But in the beginning, it's hard to remember that the lower the pH, the more concentrated it is. Now, another thing I want to mention before I get off of pH is pH, the range, go back to pH here. pH ranges from -2 to 14. Now, in some classes, they say you can't have a negative pH. That's totally incorrect. Negative pHs are just strong acids. You can have -12. Because when you have the negative of a negative, you really have a positive, and that's why it gets big. So the range, and then right in the middle is pH 7, which splits the base from the acid. Okay, all right. Does that make sense? So pH is. Okay. Now let's talk acid solution. If I took hydrochloric acid, let's say I have 10 grams HCl in so we have a total solution. That's total volume now. Total volume of 4.12 liters. What is the hydrogen ion concentration? Okay. All right. So I'm going to dump in 10 grams hydrogen. So, by the way, a shorthand way of writing concentration is square brackets. So that would be the concentration of H plus. Okay, well, concentration is moles per liter. We've got grams, so we've got to convert the 10 grams of HCl to moles of HCl. Now, before we go on, I'll remind you, hydrochloric acid is a strong acid. That means as soon as we put the hydrogen chloride or the hydrochloric acid in water, there is no more HCl, only H's and Cl. So if we know the moles of HCl we put in, that's equal to the moles of H. because the ratio, stoichiometric ratio is 1:1. And that's also equal to the moles of chloride. How many moles of HCl now are in the solution? How many moles of HCl are in the solution now? Say I put in 5 moles of HCl, dump that into, it's a gas, but I just dump it into the water. How many moles of H do I have? Don't need your calculator for this. 5. 1:1. How many moles of chloride do I have? 5. I start with 5, 1:1, so I have 5. How many moles of HCl do I have in the solution? 0, because it's all dissolved. There's none left. Okay, so if I start with 5 moles before I put it in the solution, once it's in the solution, it dissolves and goes away. We have H's and Cl's left. Okay, so now the final concentration is supposed to be okay, so let's look at the final concentrations now. HCl is 0 moles. Final concentration of H is going to be 5 moles. Final concentration of Cl is going to be 5 moles. Okay, keep hammering that in. It's crucial to understand that any strong acid comes apart when you throw it in water. The water rips it apart. The solvating force of water is really strong with ionic compounds. That's why they dissolve. And we'll see with double replacement, not all dissolve, but a lot do. Okay, acids in particularly dissolve because H plus and water is quite stable, so they come apart. Okay, is this clear that we have no HCl left? Okay, now with HCl, we only have one acidic H. Hydrogen, we have 2 acidic H's. So let's look at sulfuric acid now, real quickly. Okay, so up here we balance the equation. 1 HCl, one of these, one of these. Okay, so let's balance this equation. Is this one balanced? Well, how many H's do we have on the left? 2 on the right, 1. Now we have 2. How many SO4s on the left? 1 on the right, 1. So it's balanced now. So if we have 5 moles of this, how many moles after we mix it up? How many moles? So this is the initial concentration. So what's the initial concentration of H's before we add the sulfuric acid in there? Well, we haven't added anything in, there's nothing there then, right? That's gonna be 0. Okay, now let's jump into sulfuric acid. So our final concentration on sulfuric acid is gonna be 0. Again, because it's a strong acid now. So how many moles of H plus do I have? What's the ratio from the balanced equation? It's 1 to 2 to 1. 10. And how many moles of sulfate ion, SO4? 5. Now, look at the big difference between HCl and H2SO4. Sulfuric acid gives off 2 per mole. So that means it's going to be twice as many H's. Phosphoric acid is a triprotic acid, gives off 3. Citric acid, triprotic acid, gives off 3. So we're going to be working with hydrochloric acid, monoprotic, meaning it gives off 1. Notice I say monoprotic. Protic is the same as proton. So monoprotic, diprotic, triprotic. Okay, so does this make sense on this initial and final concentration? Sulfuric, because it's a diprotic, is a 2 to 1 ratio. Okay, so let's continue with this initial problem here. Heck, let's rewrite it up here. We have 10 grams HCl. Okay, so we want to know concentration of H plus. Remember, square brackets or concentration in moles per liter. Okay, first thing we need to do is convert grams to moles to find out how many moles of HCl are going to be thrown in that solution. Okay, let's see. Hydrogen is 101. Chlorine, is that 3545? Yeah, how about that? Okay, so we're looking at 3646. Okay, so we're going to take the 10 grams. To moles. Okay, from the balanced equation now, the balance, is it balanced as written? Yeah, balanced as written. 1H, 1H, 1Cl, 1Cl. So it's balanced as written. So this is HCl now. Okay, so we need the H plus over HCl, so our units cancel. So let's do Okay, so that's the moles of hydrogen ion we have in there. How many moles of HCl is in there? Zero. There's only H and Cl in there. No HCl. Okay, so we've got okay, so hydrogen ion concentration is 0.06, that's two sixes. 0.665 or 6.65 times 10 to the minus 2. Okay. You're in 1A, 2A, or 3A. You would then take this and convert to pH. So we take the negative log of 6.0665 on your calculator and take the negative of it, and that would be pH. It's a simple one click. That's why don't they teach it? And they get upset if I taught pH. They're saying that's out of the scope of the class. The student learning objective does not include pH. Oh, by the way, Saturday lab people's test 2 scores got removed. I don't know why. So look on Canvas if you're Saturday lab, and I've entered some back in, and some people from Saturday were in Friday's lab yesterday. I entered it in for them. So just look on your Canvas. If score's missing, you need to tell me in lab today, okay? And I have some tests to return as well from Saturday. And I don't know. I have everyone's, I copied them all because I have to do that student learning assessment. So I've copied all your tests. It's just that it's easier if you just tell me. Otherwise, I'm going to look it up with the PDF file. And anyway. Okay, so are there any questions about how I got this? Okay, it's important to understand the mole part because we start neutralizing. I'm going to throw in moles of base, moles of acid. And usually they're not equal. Okay, so let's do one of those. Okay, so I've got okay, so I've got 5 moles of HCl I just put in here. And this is The solution is 1.2 liters. Now I'm going to dump in to 2.4 liters. And I'm going to throw in 2 moles of sodium hydroxide. So what's going to happen? Well, the acid and base are going to be neutralized and get very hot. One of the outcomes of a neutralization reaction is heat. And the reason why it gets hot is because the resultant water formed is very stable. I want you to keep in mind that the result of a reaction that creates a very stable product produces heat. Okay, so we've got HCl plus NaOH. What does that make? Well, it's really not H plus, I mean HCl, it's really H plus Cl minus and Na plus OH minus. Remember, because these are strong bases, strong acids, so they don't exist separately. So when we put those together, the H and the OH create water, hence the neutralization part, plus what's left over, which is sodium and chloride. So this is considered a salt. And remember, salts are very generic. What a salt is an ionized compound in water. Any ionized compound. It can be George and Emma, and if they're ionic, they're salts. Okay? So it just happens to be sodium chloride is common table salt, but it isn't just sodium chloride. Okay, and this, of course, is good old water, extremely stable. And this would be the acid, strong base. Now this calculation is going to be made very simple compared to what it is if it's not a strong base and strong acid. Weak bases and weak acids are very complicated reactions. It ends up being a quadratic formula you have to solve, and it's much more involved. It's like going from simple stoichiometry to limiting reagent. That much of a jump. And I think it's because it's a quadratic equation, then you got to use a quadratic formula. Why am I going on and on and on and on? So weak acids and bases are a pain. Strong ones are very, well, you may disagree, but strong ones are very straightforward. Okay, so is this balanced? Don't everyone answer at once now. It'll get confusing. Well, how many H's we have on the left? 2. How many on the right? 2. H2O.
Is that just one or you have two?
Yeah, there's O and 2 H's. So how many H's is that?
Oh, I was confusing the N in the salt. I was confusing the N.
Yeah. Okay, so it's balanced as written. So super simple. Okay, now, if it's balanced, remember the balanced equation is a molar relationship. It's also a molecular relationship. That was the question on the last test. Okay, what can we gain from a balanced equation? 2 things. Okay, so we've got moles already. We've got moles of HCl, right? Five moles of HCl gives us how many moles of H plus? 5, because it's 1 to 1. One HCl gives us one H plus. Okay. And we have 2 moles of sodium hydroxide. How many moles of hydroxyl ions do I have? 2, 1 to 1. Okay, what is the ratio of H and OH? Is it 1 to 1, 1 to 2, 1 to 5, 1 to 10? What is it? When you form one water, how many H's? How many, if you want to form 1 mole of water, how many moles of acid do we combine to make that? 1, because it's 1 to 1. So we need 1 mole of H's, 1 mole of OH's gives us 1 mole of water. That's what our equation says here. 1 of this, 1 of that gives us 1 of that. Okay. So how many moles of water do we form? Start with 5 H's and 2 OH's. 2. Okay, this is like our limiting reactant problem from the last unit. We're not done yet. If we have 2 moles of water, is there anything left over? Huh? We have salt too, but how many moles of H plus do we have left over? Unreacted. We start with 5 and we use 2 of them. That leaves 3 left over. Okay. Now, it depends on how much acid and base. If there's more base than acid, moles wise now, then we'll have a basic solution. So this is base or an acidic solution because they have more H's left over. So what is our new concentration of H plus? Okay, so we know we have 3 moles. What's our new volume? What is it? 2.6 liters. Excuse me, 3.6 liters. Okay, 1.2 liters, 2.4 liters. Okay, so I got that by adding the acids liters and the base liters. So our concentration, our acid concentration okay. Any questions about how I got the 0.83?
The 8.03 moles per
This guy here?
Yeah.
I divided 3 by 3.6. 3.6, because we started with 1.2 HCl, 2.4 of sodium hydroxide. So together 3.6. Was that your question? Okay, cool. All right, now we can continue on here with the same problem. What is the concentration of well, chlorine comes from the acid, the HCl. How many moles of acid do we start with?
5.
Excuse me, 5 moles, yeah. It's 2 moles of the base. 5 moles of acid. Okay, how many moles of Cl comes from 5 moles of acid? 5, this is 1 to 1. And that's the only source of chloride. That gives us 1.4 moles per liter.
Concentration of Cl, yes, solution.
Okay, let's do it for sodium now. Okay, we have 2 moles of sodium hydroxide and it's 1 to 1. So how many moles of sodium do I have? Starting with 2, how many moles of sodium do I have? 2, right? How many moles of hydroxide do I have left over? Good question, you guys. All right, we made water with it, right? How many do we have left over? None. All used up. This is like limiting reactant. But what's limiting the production of water in this situation is hydroxide or sodium hydroxide in this case. Yeah. This is about as complicated as we're going to get for acid-base solution calculations. Now, the only one is going to be mathematical is the titration calculation. We haven't talked about that yet. Our last lab is a double lab. It's lab 15 and 16, I believe, but anyway, it's a titration lab in 2 parts. And we're doing it all in one day. And it'll be similar to this, because it's going to be an acid-base neutralization reaction. But with it, we're going to stop when the acid equals the base. Here, we went beyond it. Okay, now the other complication on this would be, instead of moles, I said they're grams. You have to convert to moles. Because it's always moles. We live in a mole-philic environment. Okay, now there were a lot to these guys. Are there any questions about how are we doing on time? Let's see, almost 1 o'clock. No one has any questions about this guy? All right. I want you to review this. Go over all these steps again. It's not a lot of hard steps. It's just a bunch of little steps. That's what makes this complex. Okay. I want to talk about one more little slight. When we put hydrochloric acid in water, it doesn't quite yield H plus and Cl minus. There's a little nuance that some textbooks use it and some don't. So the H plus and the H2O form something called a hydronium ion. That's what really happens in water. So the H is tied up with the water itself, the H plus. Because H plus by itself is not all that stable, but once it ties up to the water, it becomes very stable. So whenever we see the H plus, we're really talking about H3O plus, the hydronium ion. And some textbooks use it, some don't, depending on the class you're in, the instructor you have. But I want to mention that's what's happening really. It's just that whenever anyone does calculations, they never include hydronium, they always include H plus. And there's something, the bond between the H plus and the water, there's a very special type of bond. It's called a coordinate covalent bond. And that's what makes that bond. And they're used fairly regularly in organic chemistry, for sure, particularly in pharmaceuticals. They use a lot of coordinate covalent nitrogen bonds with H. Okay, so that's what I wanted to cover today. What I'd like you to do is really spend some time on this last problem and make sure it's clear, okay? And then, okay, so next Friday, I'm going to cover double replacement reactions. And on Saturday, I'm going to go over this and we'll have our test the following weekend.